Today, I'm going to give you an overview about AI accelerator chips for training large language models from my understanding. This video is purely to educate the beginners in this topic.
So let's dive into
Following
the
the
topic.
success of models like ChatGPT, research into large language models has grown rapidly. Today, we also have multimodal LLMs that can handle text, images, audio, and even video. But this comes at a cost, requires massive amount of data, compute power, and energy. To do this, general purpose GPUs are widely used because they are versatile and readily available. But they consume a lot of power and generate heat, which makes cooling expensive. That's why companies are now designing specialized LLM accelerators. These chips use dedicated circuits that make them much more efficient than general-purpose GPUs, reducing cost and speed of designing
Training.
AI accelerators. Engineers focus on four main goals: throughput, efficiency, scalability, and flexibility. The idea is simple: do more math, use less energy, work smoothly in clusters, and support multiple data formats. These goals keep chips both powerful and practical for training very large models. Inside these chips are specialized compute units like tensor cores optimized for metric operations. They are paired with high bandwidth memory which moves data at terabytes per second. Since training runs on many chips, they need custom interconnects for fast communication. And finally, a smart memory hierarchy ensures data is always close to the compute units, preventing single
Slowdown.
chip is not enough. They have to scale across entire data centers. That means designing for cluster performance, managing huge power and cooling needs, and making sure AI frameworks like PyTorch, TensorFlow run smoothly on the hardware. Without this system-level integration, even the fastest chip won't reach its full potential. We look at the industry examples. NVIDIA H100, one of the representative LLM accelerators, is officially supported by various frameworks due to its widespread use in LLMs. NVIDIA provides dedicated framework like TensorRT LLM and performs computation acceleration through the NVIDIA CUDA library. The second one is Google's TPU pods scale thousands of chips together for huge workloads. And the third and the last one, Cerebras took a radical path. Instead of many small chips, they built a single giant wafer scale chip with almost a million cores. Each approach is different, but the goal is the same: push AI performance higher. Building these chips is extremely expensive, and engineers must balance flexibility with specialization. Two specialized chips less useful beyond LLMs, and two general chips lose efficiency. If we look into the first challenge, memory, as the scale of LLM increases, the required memory capacity also grows. If we look into the low power consumption, the total system power consumption increases sharply as multiple accelerators are required for LLM services. Scalability: most LLM accelerators use interconnections developed by each manufacturer. Executing massive LLM models on a single accelerator is challenging. Therefore, interconnection technologies are crucial for scaling up by connecting multiple accelerators and scaling out by expanding these connected accelerator groups. Software compatibility: most LLM accelerators use proprietary software stacks. Providing a seamless development environment is essential as many users rely on frameworks commonly used with GPUs. Furthermore, while support from existing frameworks for LLM accelerators is important, the most critical aspect is compiler technology that allows developed models to perform optimally on LLM accelerator hardware. AI accelerators are the engines of modern AI. Without them, training today's massive LLMs would take years instead of weeks. They are not just faster chips, they are the foundation that makes the next generation of AI possible. By comparing the specifications and performance of major accelerators, we identified current technology trends and issues such as memory capacity, power consumption, scalability, and software compatibility. Future research requires innovative hardware designs and software optimization technologies to address these challenges, focusing on enhancing energy efficient and scalability while ensuring software compatibility. I hope you understood the topic. Let's conclude the video. Thank you.